So as I promised last week, I'll quickly go through an example of report covering the practical activity we perform on the graphical characterization of stream flow regime through flow duration curves, construction for gauge sites, and prediction in case we deal with an ungauged river cross section. This is an example from one student who attended last year. As you can see, she starts by illustrating very briefly and quickly and schematically the study area and available data, which is something I suggest you do as well in case you have any doubts during the oral assessment, since we will discuss your reports together with addressing some theoretical questions and topics. As you can notice, she presents a report that focuses on the smallest catchment we have in the study area, renal trachea. So during the practical activity, if you recall, we always consider Sabia San Carlo as the target site. She is instead focusing on the construction of flow duration curves for the site and also the prediction, pretending the site itself is engaged. She defines theoretically the different interpretations of flow duration curves that we see during the course. Hello, good morning. She reports the mathematical expression we use to quantify the duration all the way to plotting position. It's always good to have it there in case you forget some passages and the steps to build the curve. Graphical example with caption for the diagram, then annual interpretation, construction for empirical data, then percentile flow duration curves, their definition and the link with the return period, something that we see. This is still a theoretical description, representation of the percentile curves, and a comparison of the different interpretations. So things that we addressed during our practical activity in the classroom. Then the construction of a regional model, the two elements that are considered in the regional model we studied, a dimensionless flow duration curve and a predictor of the mean annual flow, the index flow, through a multi-regression model. The first part focuses on hydrological distance and prediction of dimensionless flow duration curve, the discussion we had on catchment descriptors, the fact that we need to standardize them in order to remove the inflating component given by the different units and range of variability. A table that illustrates the hydrological distance with the site of interest, different numbers, but of course she's focusing on a different site. The weighting scheme that we use, so the formal definition of the weights and the weighting scheme, and then the construction of the empirical dimensionless curve, the empirical curve for the target site, and the predicted one. Okay. And finally, the multi-regression model for predicting the mean annual flow. So the stepwise regression analysis and the analysis of all different models with increasing complexity. One variable descriptor, two variable descriptor, until we reach the highest level of performance. In the case also, a three predictor model was not better than a two variable one, so she opted for actually the same structure that we identified for a different site, for site number 5. She worked on renal trachea instead, but the structure is the same, catchment area and mean annual precipitation. a table summarizing the predicted mean annual flow values and the empirical ones. So all the rows with a white background are the data actually used to build the model. Instead, the first row is the one focusing on the target size. So this data here was not used for constructing the model. Okay. The scatter plot representing the performances of the model for the target site. Here, the performances in terms of the prediction of mean annual flow is not as good as the one we identified. It happens. This is why you cross-validate your regional models, leaving out the site and rotating them. And this is a comparison between empirical and predicted. In her case, it may happen by chance. In her case, the prediction in the low flow region is actually very good, because the model for predicting the mean annual flow performs poorly, and so by chance the result is that the low flow portion, the most critical part of the flow duration curves, is actually the one that is best reproduced, very well reproduced. But this is because two errors compensate: the error in the low flow portion of the dimensionless curve, and the error with a different sign in predicting the mean annual flow. Okay, so this is a presentation of all the activity, and if you note, the structure of the report is rather chronological, step by step. All the things we did for a different site, she repeated for site Reno and okay. She didn't change the interpretation of the curve. She still focused on the median annual flow duration curve. Another thing you may vary if you want is the interpretation of the curve. You can consider period of record instead of median annual, for example. Okay, is this sufficiently clear in terms of the report structure? Yes, on 3 different occasions we covered all these aspects during practical activity in the classroom. Yes, but you will have to look at the recordings. In the Quale webpage, there are the recordings of all the classes. No? No, but this is probably a matter of permissions. Please, repeat me your name, please. Julie? Julie. Okay, please, Julie, check right away, because in case you don't see the Panopto portion of the virtual page, I may need to change something in the Panopto application, giving you access to all the recordings. If I change my role in student, I should see what you see. So here on the side, it's not visible via browser when I open it, but here on the side you should see all the classes recorded. Can you, by the end of the class, check so that I understand if I have to, let's say, give you some authorization. Also, another thing I'm asking you is to fill the online form, so I keep track of the students who attended this year. This is a shared folder you can access, and here this is good also for you that you refresh these things. You will see here in the share folder material that were created during classes themselves. So, for example, notes when we were working in R. I took note of notes that while we were working in R the first times, I took notes explaining different functions. There is also picture of the blackboard that Reza took during the last class. Okay, so things that we produce during classes that might be useful end up here. Did I close the visuale? Yes, I did. No, I didn't. I have to remember to go back to my. Okay. Concerning the report structure, everything is clear. Do you have any doubts? Good. So we have 3 theoretical topics to cover, not as extensive as the one that was focusing on the graphical representation of stream flow regime. We will start today. I hope by the end of the class we will touch 2 of these, 2 out of 3. The environmental flow, definition and estimation, some basic hydrological tools in GIS environments, and then the last topic we need to address is designing, sizing the reservoir capacity for power plants that do have a reservoir, because the goal there is to control the inflow so that the turbine flow can be kept constant throughout the year. This is something run-off the river power plants cannot do. They divert water when the water is available in the stream. Okay, these are the 3 topics. There's a short practical activity associated with the reservoir sizing, which will be the last practical activity of the class. I hope I'll have enough teaching hours to cover this properly. And there's also a practical activity on the GIS application that focuses on river network extraction and watershed delineation, starting from digital elevation map. Okay, so this is why I hope to cover this theoretical part today, because in this case we were able to start on Wednesday right away with the practical activity on GIS. Therefore, it is fundamental that you bring with you your laptop on Wednesday, and the laptop has to have QGIS installed. Okay, you do have 3-point-something version already installed. It doesn't have to be the very latest long-term release. The important thing is that it's beyond 3.14, I think, when I constructed the project. Good. So, let's start. Environmental flows. Do you have an idea what an environmental flow is? You already heard this term or never? Or e-flow, so something we go by short indicating e-flows. E-flows normally are discharges, stream flow values that are identified by the water management authority in order to preserve the well-being of a natural habitat, but also the ecosystem services that the habitat provides us with. Okay? Here you have the definition. These slides I'll be showing today are rather dense in terms of text. I will focus on the things that I consider to be the most important ones. Of course, the text is rather detailed, so they can be used also as handbook for this part of the course. So here you have the definition. E-flow, a particular flow regime in a river which is capable of sustaining a complex set of aquatic habitats. As you know, as we know, rivers are the places where different species, different biota develop and grow. Biota is the complex of the living things in a given natural habitat. And thanks to these complex system of aquatic habitats, we get as human beings also services from the habitat itself. Preserving the habitat, the biodiversity, and these ecosystem services has to do with the preservation of at least some part of the natural stream flow regime, because it's rather evident that if we divert in time the discharge flowing in a natural stream to send it to a power plant as a turbine flow, then we kill the ecosystems and aquatic habitat. So it is, let's say, safety measure the water managers have to keep control water quality, the well-being of a habitat, and the well-being of living things in the river system itself. You know what ecosystem services are? Can you provide me with examples? If you haven't looked at the slides yet, of course. You know what they are? Those are services to us, human beings, from our natural environment. In particular, if we focus on rivers, I lost track of my mouse, but I'm sure I will come back by the end of the class. Maybe, or maybe not. This is weird because the next slide is not particularly heavy, it's just text. Okay. Maybe we're getting there. Okay. I don't know what happened. Sorry about that. Ecosystem services examples. So let's be selfish. Let's look exactly at services to us. The fact that we can navigate a reach of a branch of a river, so use the river itself as a means of communication, is a service. If there's no water, we cannot navigate anymore. If there's no water because we diverted it all to produce electric energy for a reach of hundreds of meters, then we don't have that service anymore. The same goes for fisheries. And the preservation of fish and wildlife and preservation of biodiversity is also associated with the possibility to preserve, the possibility to use the river as a source of food. Okay, recreational characteristic features associated with natural environments. Waste assimilation, of course, having water in large amount and natural stream flow in large amount enables the river itself to assimilate and regenerate the waste we might end up inputting in the river itself. Water supply, so the fact that we can use water for example, drinking water, or for example, agricultural purposes. Of course, it's a multi-objective optimization problem in which we have to evaluate all different services and the fact that if we abstract too much, we end up interrupting, discontinuing these services themselves. Okay, sufficiently clear? These are examples. Focusing on fish and wildlife conservation and the fact that our activity and presence and the services we request from natural environment impact species, I think this image here is particularly informative. This is probably one of the most important issues we address when we set an environmental flow. Quota of river discharge we do not want to touch. We want to live in the river. This image is a representation for different hydroclimatic areas of the world, near Arctic, the Paleo-Arctic region, this blue one, Neotropical, Afrotropical, Indo-Pacific. These are macro hydrological and climatic regions in the world that are analyzed in a study by the World Wildlife Foundation through a dimensionless index they term Living Planet Index, LPI. This is a clickable link if you want to see the definition of this index. The original paper is fully accessible. It's a standardized index that looks at the distribution in terms of the overall number of vertebrates of living things. And in particular, these diagrams go from 1970 all the way to 2014. You have the average index. One refers to the origin in time. And then you have the evolution in time of the average value, it's the white line, and also the uncertainty, because quantifying the overall number of living vertebrates is not an easy task. So you see some uncertainty, but what is the most striking feature of all these, well, almost all these 5 diagrams? What is the most striking feature? The overall decline of the number of living vertebrate in all these areas. The one that is more or less the most stable, but still you see an evident decline, is this region here in blue. Other than that, there is a huge decline. Look at what is happening in the Latin America continent here. The impact is very, very dramatic. So we are witnessing a tremendous decline in terms of biodiversity and number of things in natural environment. That's part of the reason why we started, not a very long time ago, we started setting some rules that quantify the amount of water we can use from rivers. E-flow itself is a term that dates back less than 20 years ago from an international conference held in Australia. The community of researchers, policy managers came up with this declaration defining environmental flows, describe the quantity, quality, and timing, this is very important, timing of water flows required to sustain freshwater ecosystems. And this you can summarize in ecosystem services. Terminology evolved in time, and nowadays there are still synonyms that are used and that mean more or less the same thing. Environmental flow can be referred to as in-stream flow need or ecological reserve. These are all stream flows that we want not to divert from rivers. Ecological demand of water, environmental water allocation or requirement, and these are probably the oldest terms used and introduced: compensation flow or minimum flow. Minimum flow underlies a different perspective. We find references to environmental flows in global initiatives, global regulation, national and regional regulation too. The first reference I want to make is the Sustainable Development Goals from United Nations. In particular, we find explicit reference to environmental flow in the Sustainable Development Goal number 6, access to clean water and water sanitation for all, and in the subtask 6.4 and 6.6. In particular, increase water use efficiency. If we increase water use efficiency, we need less water, and therefore we can use less water from rivers and natural streams. And protect and restore water-related ecosystem. One of the overarching goal of goal number 6 is to bring back to good environmental quality all the aquatic systems on Earth, possibly. And the only way of doing it is, of course, to use less water, use water in a more efficient way, and set up norms and regulations that prevent uncontrolled human use of natural stream flows. Just to provide you with an example of our global water demand, this is the water demand in 2000 and a projection, so projection is of course highly uncertain, up to 2050 in 3 different groups of users across the world. So this OECD is Organization for Economic Cooperation and Development. I think this link should work. So the, let's say, dark blue countries belong to the OECD. The light blue ones are countries that apply to be included in the OECD. Then here you have BRICS, Brazil, Russian Federation, India, Indonesia, China, and South Africa, and this is the rest of the world. The projection of water use, global water use, this is very impressive because these are cubic kilometers of water, is projected to decline. Let's see if this projection is accurate, because in reality, globally, our water demand and water withdrawals are constantly increasing with a pace that is rather significant, 10% every 10 years. In other countries that are witnessing their industrial boom, like, for example, BRICS organization, you can see the projected change is dramatically increasing, doubling. Each bar is divided in 2 colors. Colors are the main uses, so irrigation, domestic, meaning water supply, for example, drinking water supply, to grow livestock, manufacturing, so industry, and electricity production. As you can see, overall, as I said, the projected change is increasing and quite dramatically. This is why we need to set rules on water use. We started a long time ago. The definition of environmental flow is rather recent. Ecosystem services were not even theorized in the 70s, but researchers like Hoff were starting to addressing this term, and let's say interpretation and concept changed a lot, because in the 70s the most general term was minimum flow. The idea is, let's use as much water as we can, so we leave in the river the minimum flow. Now the interpretation moved to environmental flow, so something that ensures the well-being of the environment. how these discharges are identified by water managements and water authorities. There are basically three different ways to set environmental flows. You find them listed there, and the complexity of the method itself increases going from the top of the list to the bottom of the list. The most simple method is termed hydrological method. Then you have hydraulic habitat methods, and the, let's say, also most up-to-date method and most complex one is the holistic method. Okay, a couple of words on each and every one of them. Hydrological methods. These are the original ways to define ecological flows, but they're still very, very used widely across the globe nowadays. They're easy because they just need information on stream flow regime. They just use discharge data to be applied. And common examples are stream flow indices. So one may use Q95 as the environmental flow not to divert, to leave in the river, or some fraction of the mean annual flow, the long-term average. 20% of the mean annual flow is another common index used as environmental flow. Hydrological method, because we're not looking at anything else. We're not really looking at the well-being of fish species, for example. We say, okay, we have some stream flow in the river. If we try to prevent going too much down, so taking mean annual flow as a reference, it's a natural characteristic, and setting the environmental flow a fraction of it, perhaps, we will also protect the environment. But there's no objective evaluation of that. It's just very simple. And experts are advised to have a characterization that is based at least on a few years of continuous observation. It would be best to have 15 years of observation to use hydrological methods, but I want to stress the fact that hydrological methods are very, very subjective. There's no objective criteria in it. Hydraulic habitat method. Associated with a given stream flow, you also have a portion of the river cross-section that is wetted, okay? And if the stream flow is low, you have only a fraction of the river cross-section that has water. But if the stream flow has lower, well, I hope, at this point of the class, the course. But as the stream flow increases, more areas, wetted areas, becomes available. Typically, the bank area that are flooded seasonally or rich of water only seasonally are where spawning happens for fish species. The reproduction take use of these areas with calm waters and low speed. So hydraulic methods combine the two elements, the hydrological variation of the stream flow regime and the fact that from a hydraulic point of view, associated with a given stream flow regime, you have a given fraction of the area that becomes wet. And a very common approach to use hydraulic habitat method is to look at the relationship between discharge and some hydraulic parameters, okay? Here you have an example of the wetted perimeter. The wetted perimeter, depending on the water depth, is the portion of the river cross-section that has water. And normally, natural river cross-section show behavior like this. Discharge increase, and initially, for a given distance, discharges are increased. You see, of course, an increase of the wetted period, but the increase is very slow. Then, as soon as the floodplains get flooded, the wetted perimeters increase much more fast. And looking at the break in slope, it's a way to set a suitable environmental flow. Holistic methodologies, these are the most complex. Holistic because they tend to look at the problem globally. And by saying globally, I mean at all the different components. So living things, but also the fact that river stream flow transports sediment and bring these sediment to the seashores. So they look at biotic, but also abiotic components. And in order to be defined, stakeholders and large panels of experts need to come together and reach an agreement. What is at stake? What are our risks? Reducing the stream flow below a certain threshold. What are the advantages? It's a political compromise that looks, generally speaking, at all the elements that are impacted by the variability of stream flows. Okay, I do not have, since it's rather complex and it requires and setting an environmental flow through holistic methodologies requires a consensus to be reached by community members of this panel that have different interests, okay? Because a fisherman, of course, wants more water in the river and a seasonal variation that mimics the natural one, so reproduction seasons are not impacted. Instead, the water manager in charge of managing the power plant has completely different interests. Regular flows, so it requires me reaching a consensus. I don't have a general example, but I will show you in the reminder an Italian example of what an holistic approach means in setting an environmental flow. Of course, as I was saying a few minutes ago, environmental flows are referred to in national, regional legislation. In the European Water Framework Directive is ubiquitous. It was launched in year 2000 and updated in 2015 and had a direct impact in region in the way environmental flows are set, as you will see in the example. This table, which I compiled 2 years ago, so might be not exactly up to date, shows you how diverse the global situation is when it comes to environmental flows requirements. In these columns, yes, no, indicates if a country or a region has available legislation to identify environmental flows. And you see that very big players, for example, do not have yet national legislation available. Where this doesn't mean that India is huge. It's really big. It's a continent, right? So India itself has several nations inside, and this doesn't mean that they do not have any sort of regulation altogether. Next column here indicates the prevailing approach, most commonly applied method, And of course, we see regions where holistic approaches are implemented, but you see that in several places, the most simple approach is still largely used, the hydrological method, looking at the variability of stream flow and setting a given percentage of the mean annual flow as an environmental flow. And then you have some notes and details about different realities in different areas. This is the Italian example. Since the Water Framework Directive was entered into force in the European Union, it's a directive, it's not a national law. State members started to develop their own laws, internal laws and regulation, in compliance with, of course, the European directive. And you see how many years have passed since the introduction of this criteria in the Water Framework Directive and the actual implementation and enforcement into national and regional law, 17 years. Nowadays, in various regions of Italy, all of them nowadays, according to the Water Framework Directive, an holistic approach to the definition of environmental flow entered into force. And here you have an example on how to compute environmental flows that comes from the Marche region, the region next door to Emilia-Romagna. The environmental flow is computed using a multiplicative expression. Okay, you see the mean annual flow. This is the only term that has the discharge units, cubic meters per second, mean annual flow. Then there's a term here, K, that is an empirical coefficient mapped across the Marche region that, depending on where you are, may vary between 5% and 10%. So this part here, this is the environmental flow according to a hydrological criteria. Okay, 10% of the mean annual flow. All other terms look at other different aspects and mostly, as you will see, increase the basic estimation from hydrological flow, meaning that all these terms, B, E, the maximum between N and IF, G, T, these are all dimensionless terms, multiplicative dimensionless terms that are, as you will see, in most of the cases, larger than 1. So you start with the hydrological environmental flow, and then you increase it, looking at different elements. For example, B is an hydrogeologic index, okay? And it varies between 1, you do not touch the hydrological environmental flow, 2, twice as much, because in the area you have regions where geological units are mostly fractured limestones and there are karst phenomena. So you have rivers in the surface, and then for some portion of the river itself, part of the water starts to flow downstream in natural tunnels, in karst tunnels. So you want to preserve water, otherwise you will not see water flowing on the surface anymore. So you take the hydrological environmental flow and you increase it by 100% in the most delicate districts. Okay, this is the rationale. If your stream is in very good condition, E, for example, is equal to 1. But if it's polluted, if it's impacted, and you are trying to reconvert the status, bringing it back to good, according to the Water Framework Directive, and you add another 40%. Okay. T. I want to spend also a few words on T, because with this new system, environmental flow became seasonal. So environmental flow varies for different reasons, for different seasons. So T is a temporal factor that identifies the flow season in different seasons that the norm sets out. So this could be, let's say almost autumn. This could be winter. This could be spring and summer. This is the duration of these seasons, and this is the value of T. So in some seasons you increase again by another 30% your initial prediction. In winter time, you increase by 50% your initial prediction. Okay, so you start with a minimum amount, which is 10% or 5% mean annual flow, and then multiplying it by these terms, you inflate a lot this stream flow, bringing a further protection to the natural stream. What does it mean? Here you have a few lines that indicates rivers in Marche district where run-of-the-river power plants are present. This is the hydropower plant in these four examples. You can have a detailed description of this study, which I performed together with Serena Ceola a few years ago. And asked by Enel, which is the main player in Italy when it comes to hydropower production, we wanted to see the impact of this new regulation on the hydropower potential on existing power plants, run-of-the-river power, mostly run-on-the-river power plants, switching from the pilot situation where no regulation was present. There was locally, regionally, some environmental flow requirements set by the local administration, which predated the Water Framework Directive. So it was mostly based on the observation of natural streams, and it was constant throughout the year, a single value across all 4 seasons. These were the values that were used before 2017, okay, for that power plant. So 0.25 cubic meters per second. And this, in the 4 seasons, where the environmental flow that needed to be enforced after the entry into force of that regulation. You can easily tell how big, how huge this impact was for power plant managers, because this was what they used to release, and this instead, it's the new reference value in the 4 seasons. In some cases, it's 3 times more. Okay. This, of course, has a huge impact on the hydropower potential, reducing it significantly. And from what we could tell, according to the existing literature, not as such an evident positive impact on the well-being of 2 different fish species. Application example, and then we stop for a few minutes before radically changing the subject. This is another run-of-the-river in the same district, Marche region, Abbadia di Naro. You can see the weir. You can see the stream, downstream the weir, The wear is there because part of the water is diverted through these artificial channels to the hydropower plant. Of course, setting an environmental flow protects the branch of the river downstream the diversion. This can be a few tens of meters, but in some cases the flow is returned to the original river only kilometers downstream the diversion. Okay? So even if we do not have a reservoir, even if these are run-of-the-river power plants, they do impact a portion of the reaches that can be longer or shorter depending when we return the flow into the river system itself. Okay? Graphically, because if the plant is of the kind run of the river, you can use flow duration curve to assess what is happening, setting a different environmental flow. And this is what we did with Serena Ceola in that study. If you are interested, go and look. I'm referring to her by name because I think she's a professor of some of you, or not. Serena Ceola. So I'm just you? And you. Okay. So, for Abbadia di Naro, in the cross-section where the diversion is located, this is a representation of the natural stream flow in terms of period of record seasonal flow duration curve, meaning that it looks only 3 months time. Puts together all the observation available, look just at spring for every year, and construct this flow duration curve. If you want to see what happens when you set an environmental flow prescription, you have to identify as a horizontal line your environmental flow. In this case, for that season, I don't remember which season was, this is set by the regional authority, the environmental flow. Of course, you cannot divert anything for 20% of the time in that season, right? Because your natural flow goes below the environmental flow. Is this sufficiently clear? But not only that, because in that case, power plants were already existing. So they were already running some turbines with some specs. And I don't know if you know, if you don't, I'm telling you now, turbines have a minimum flow requirement, meaning that if the discharge is below some threshold, the turbine doesn't work, okay? In this case, the minimum turbine flow threshold was 1 cubic meters per second. So on top of the environmental flow, you have to place the minimum turbine flow, right? Another horizontal threshold that tells you right away that your power plant works for less than 60% of the time of that season. Okay, you see this? Because you have to fulfill the environmental flow requirement, and then on top of that, you have to have another extra 1 cubic meters per second to use your power plant and produce energy, which identifies the volume of water that can be used according to the environmental flow prescription. You don't have only a minimum flow for the turbine flow, you also have, like for the Paul River example, we saw a few classes ago, you also have a maximum turbine flow. In this case, you cannot divert and use more than 8 cubic meters per second. So the grayish portion under the curve is proportional to the volume you can use. Okay, performing this kind of assessment with all the 4 seasons indicates the volume of the water you can use according to the new environmental flow prescription. And in the paper, we converted this using coefficients into hydropower potential you can produce. Changing the environmental flow setting turns into a reduction or an increase of the water volume you can use and impacts, of course, the hydropower potential. We made a comparison in the study. I think if you are interested, you can have details there. We made a comparison between the pilot and the situation after the water framework directive, noticing that the hydropower potential was impacted quite dramatically. Okay, everything is clear about the definition, at least at this level of detail, the three ways to set an environmental flow, starting from the simplest one, hydrological, to the most complex one that incorporates a lot of knowledge in various fields, and the fact that actually there's an impact if you protect more the environment. Of course, you have a repercussion and impact on some ecosystem services like hydropower production. We can stop for 10 minutes and we switch to the next topic in line, which is a theoretical introduction of the GIS tools that we will use on Wednesday. Okay, let's have a quick break. The first slides that are basically definitions are probably redundant and not very useful to you. So we will be using GIS environment in a very focused way, making use and showing to you how they work. Making use of some very basic GIS tools that are fundamental, though, because starting from a digital elevation model, we will retrieve, we will delineate watersheds, and using extra information, additional information, we will see how we can characterize a catchment in terms of catchment descriptors. The same catchment descriptors that we used when we set up a regional multi-regression model. You know, those terms like catchment area, mean annual precipitation at the catchment scale. Those indices are indices you can obtain, compute in a GIS environment using the tools we will be using together. So what is a GIS? You all have experiences. I'm looking here and there. Don't feel intimidated by my request. But what is a GIS? It's basically a computer program environment in which you use and you manage, you plot, you analyze data that you can represent in space, in geographical coordinates. So in a GIS, you can capture, store, manipulate, analyze, manage all types of spatial or geographical data. There are many kinds of GIS data. We will use and refer to the two, let's say, most common convention to create digital geographical data sets. Okay? So the first way is a vector model. You're aware of a vector model, what it is? All of you? In a vector model, your elements, geographical elements you work on and work with are represented in terms of their nodes coordinates. Okay? So latitude and longitude of the coordinates of each point node that creates a geometrical feature. And within vector model there are more of these, but mostly we will work with three different kind of data sets. Point data set, line data set, and polygons or area data set. A point data set is an informative layer in which you have points that can be identified in the geographical space through their coordinates and to which you associate some other information. Okay? So a point layer that can be useful in hydrology, for example, is a gauging network, a set of rain gauges. They all have coordinates and they all have additional data like the kind of sensor, like the elevation where they are installed, like the agency managing the sensor itself. Okay? In the image you have here as an example, these are instead stream gauges, so another gauging network. Stream gauges on a given river system. Then, adding some complexity, geometrical features can be lines, segments, or polylines. Okay? Here too, we're talking about vector layers, vector models. So each segment or polyline is identified by a series of nodes that are described in terms of coordinates. An example relevant to us could be the stream network, for example. So the different stream segments that compose the stream network. Information associated with each and every stream segment could be the name of the river, the location where the segment is, the district in terms of administrative district, where the branch of the river is located. And then, adding some more complexities, areas, polygons. In this case, geometrical features are polylines that start and end on the same point. So basically closed polylines areas. Examples relevant to hydrology, of course, are the watershed, subbasin, catchments that you can identify given a river cross section. So in this example here, all relevant to hydrology have a stream network. On top of the stream network, a point layer with the stream gauges, and the green lines. These are all actually closed polylines and are indicating the area draining into a given stream gauge. Okay? The red one is highlighted and it's one of the catchments in this polygon vector. In particular, is the catchment draining into the river cross-section where stream gauge 1701 is located. Characteristic of vector model is that all geographical features are associated with a given record in a table, in a digital data set. So, for example, 1701 here is this record, and these are the information associated with the polygon highlighted in red. 1701 is river or basin Bosso at the river cross-section Cagli, and it has an area of 125.7 square kilometers. Okay, this is a data set, like a data set we use in R, for example. Okay, but is connected, associated with each polygon in this layer. The sensor layer will have another data set and each record in the data set would be connected by each point in the point layer. Is this sufficiently clear? We will see an example soon on Wednesday, so I believe it will be also clear. The other huge category we will be working on are raster models. Here it's different. Here you don't have geometrical features represented by coordinates of points. Here you have a discretization of your reality into a regular grid. Okay, very often a square grid in which the information in a cell indicates the majority or the average value of a given information, the one the raster model is representing. Here in this example, I am making reference to a digital elevation model, which will be our input information we will start from for delineating watersheds and then characterizing watersheds. What is a digital elevation model? Is a representation of the topological surface discretized in elementary square cell. Each square cell is associated with a number, and the number indicates the average elevation within the square cell. That's it. They're called raster model, and another raster model example are digital pictures. Digital pictures are rasterization of the reality that associate to each and every pixel a given color in the visible spectrum, okay? Encoding it with a number, okay? It's exactly the same thing. And in fact, cells in GIS vector models are also called sometimes pixels, okay? So, are these alternative models? You can use raster model to represent something, but you cannot use vector models to represent that something, and vice versa? No. These two are ways to schematize, represent the reality. And you can decide to represent something as a vector set of layers, so with a vector model, or a raster model. Here you have a land cover digital map in two versions, a raster model and a vector model. So this is the, sorry for this elementary school drawing, but this is the reality, what we want to represent, a land cover map. So you have a river, you have woods, and you have households. And these are the two representations if you use a raster model or a vector model to represent this reality. Okay? So, in the first case, you discretize this study area into elementary square cell, and you associate a value to each cell that represents, in this case, not the average, but the majority of features in it. H stands for household, R stands for river. These could be numbers as well. I'm using letters just for the examples. T's are trees. Okay? Here, same reality into a vector representation. So, three different layers, one on top of the other. A polygon layer to represent forested areas, point layer for representing the households, and a polyline for representing the river region. Okay? So those are not alternatives, they're just two ways to represent realities, two complementary ways. They have advantages and disadvantages each. Watershed delineation would be the main task we will be doing through our GIS practical activity. I hope you didn't do that in your past academic experience, so that the practical activity can be useful and interesting for you all. In particular, we will use a very classical approach to watershed delineation and river network extraction. It's called the 8-direction 4-point model, or D8 method. It was introduced in a seminal paper 40 years ago, more, 1984, okay? And it stayed there, because back then we didn't have neither the computing capacity nor available data sets to effectively and successfully apply this methodology across large areas, okay? Starting from the early 2000s, so from 2000 on, the application of this algorithm originally introduced in the 80s boomed, and it's nowadays still widely used and applied. Are you aware of this? Did you see it in other contexts or not? First of all, I want to clarify why we call it D8 method. It works on raster information, so it uses as input and output data raster models, and it's called D8 method or 8-direction method because if you discretize your reality, rasterizing into square cells, each and every cell is surrounded by 8 other cells, okay? So the runoff that is produced in the surface can flow in just one direction. And the main assumption the method does is that it will flow along the one direction out of 8 possibilities, which is characterized by the steepest descent. So it's a gradient method. It looks for the steepest descent direction, and then it hypothesizes that all the runoff that this cell produces, the precipitation that falls here, does not infiltrate and flows over land, it will follow the steepest descent. Here you have in the slide all the steps summarized, but we will see them one by one. So there's no need for us to look at this preliminary list. The input information is a digital elevation model. So a representation of the topographical surface. Okay? Here we have an example of a digital elevation model. I'm laughing because it's a small reality, right? A digital elevation model consisting in just 9 cells. Okay? So you have some boundary cells, these, and then just one single cell in the center. But consider this as a portion of a much larger DM, okay? So, suppose that 67, 56, 49, these are all the average elevations between the cells. The first step of the D8 method is using a digital elevation model as input information, identifying for each and every cell the steepest direction, to encode and create a new raster to encode the direction in which the water flows. As I already said, the assumption we make is that the water will follow the steepest descent. So the algorithm, without us noticing, will perform the identification of the steepest descent by looking at all the cells in our digital elevation model, one by one. Let's consider this cell first, 67 is the elevation. It's a boundary cell, so it's not surrounded by 8 cells, it's just surrounded by 3. We don't have 8 cells in the surrounding because the first cell we consider is a border cell, a boundary cell. So we only have 3 options. We need to check if any of these is viable for the water flowing, because of course, if all the other cells are higher, there's no steepest descent direction. No? So the algorithm will start from this cell, looking at the surrounding cell, not 8 in this case, just 3, and look at the steepest descent direction. I see 56, 48, and 52. Of course, 56 is not interesting, right? Because we have lower elevations here, 48 and 52. So for sure, the drainage direction, it's called like that. The steepest descent direction, it's called drainage direction, will not be this, from ovest to east. No, from west to east, sorry. West to east. Because here I have, from north to south, an elevation which is lower. I'm asking you, if you are to identify the steepest descent, which one of the two would you pick? This, the cardinal direction from north to south, or this, the diagonal direction from west north to southeast? Which one? The diagonal one. All of you. You sure? I already said this when I asked, are you sure, a couple of times. It means that there's a trick there. It's not a trick. You applied a different criteria. Did you look for the steepest descent, or you look for something else in reality? You didn't look at the slope at all. You look at something different. You look at the elevation difference. It's another criterion. The D8 method used as an hypothesis that the water will flow through the steepest descent. So you have to look at slope, not elevation difference. Why am I saying this? Because if you move diagonally, then your distance will be longer than if you move along cardinal direction. There's a factor square root of 2 difference, which is 40%, a lot, right? So if you apply strictly, literally, the steepest descent method, you, actually, the computer does it, you don't have to do anything, but we have to look at slopes. So how would you compute the slope? I know you see it, but they don't. How would you compute the slope? A way to define a slope is the elevation difference divided by the distance between 2 points. Imagine to quantify the distance between 2 cells as the distance between cells centrally, right? So you take 30 meters. This is also called what? If you have a digital elevation model, what is 30 meters? How do you call it? It's the size. There's a way to call it. I'm looking for a different word. Resolution, like for pictures. A resolution of the dam is the size of the pixel. So to compute the slope, you take the dam resolution, and if you move diagonally, the overall distance would be resolution times square root of 2. Whereas if you move vertically or horizontally, the distance would be the resolution of the dm. The numerator has the elevation difference, so the slope for the diagonal direction is 0.45, whereas for the vertical direction is 0.5. So which is the higher slope? the higher slope is this. So for this cell, the computer, the algorithm, will identify this as the drainage direction, as the direction that the water flowing on the surface will follow, and will move to the analysis of the next cell, perform the same computation, identify the drainage direction, and move to the next cell, and then to the next cell. And the result will be another raster. This raster is called drainage direction. Okay? So still discretization of the study area in a grid with square cell, but in this case, the number for each pixel will be a direction, an indication of a direction. There are, in GIS system, two main conventional encoding ways. One from the Esri family, so ArcGIS, for example. One for the Gras-Tardem family, and QGIS adopts this. These numbers you see here are a way to encode a given direction as a number. So if your direction is from west to east, the code is 1. If it's from north to south, the code is 4, if you use the Esri direction encoding. Instead, if you use QGIS encoding, you have east as 1, and then all the numbers between 1 and 8 in a counterclockwise way. Okay? So, the meaning of this image is that we start with the digital elevation model as the input information, a raster in which each cell reports the elevations. And we produce a new raster, a new layer, in which each cell indicates a direction. And as you will see in the GIS, you can associate, for example, grayscale from black to white, 8 different shades of gray, and obtain images like this. This is called hill shaded relief. Okay? It's like setting the source of light in a given point and then illuminating the topographical surface. And you will see valleys and watershed divides simply by associating a gray scale to one of these numbers. Why? Because these numbers are indication of directions. Okay? So, DA method, input information DEM, first output is a drainage direction raster. So what you got from the digital elevation model is a new raster that reports this kind of information. Okay, you can see it like this, or you can see it like this. It tells you, looking at the topography, at the morphology of the surface, where the water tends to flow following a steepest descent direction. Okay, sufficiently clear. This is not yet the river network, because in order to extract the river network from here, you need an additional step. Okay, this is just a connection of all the cells, all of them, all the cells in the DEM following a steepest descent direction. Okay, so you saw numbers from 1 to 8, but what you have to picture in your head is actually arrows like that, directions. From the drainage direction to the contributing area grid. This is another raster, output raster. It is a raster that counts the number of cells that are drained by each cell. Looking at the direction of the steepest descent, for example, this cells here drains 4 cells. Why? Because it receives water from upstream, from this cell, from this cell, from this cell, and then of course it drains itself. So 4 as a contributing area is the size of the catchment that drains into that cell. It's the size of the watershed that drains into that cell. In which units? In cells. And this is also the case in GIS system. Contributing area grid will report dimensionless number, and it's the overall number of cells that drain into one point. Then, of course, if you know that the resolution is 30 meters, you have to multiply that number by 900 square meters, and you obtain the catchment area in square meter. Okay? Sufficiently clear? So we start from a DEM, we obtain a drainage direction grid. Next step, we obtain a contributing area grid, and this is not yet a river network extraction. We're not there yet. But you can color, for example, using a color scale from yellow to dark blue, the contributing area, and you already start seeing river network grid popping up, right? All cells with 1 are cells that drain only themselves. So those are cells on the watershed divide. They do not have any cell upstream draining into them. So where the contributing area is 1, you have watershed divides. Where the contributing area instead is high, very high, it means that many cells drained into that point. So it's likely that there you will see the stream network, the river. Okay? Low number, watershed divide. High number, river network. How much high? So this is a critical parameter. It's called critical source area, or critical contributing area, and it's a parameter that is used to extract a river network from the contributing area raster. Okay? For example, let's suppose that the critical source area is 10, then anything above 10 would be a pixel that belongs to the river, the stream network. In our example, we have 4, but then we move downstream and we switch to 12, because the cell receives water from here, and maybe from other cells surrounding it. And then 16 and then 25. These are all stream network cells, whereas the other ones are kill slow cells. By setting a critical source area, you can extract the river stream network from the contributing area raster. And it will be, again, a raster, meaning that it will be a binary raster. On, off, 0, 1. You have 1 if you are in the river, you have, for example, and 0 if you are on the hill slopes. How do you set this critical source area? How can you set? It's a parameter, I said, so it's something that you define, you select. What could be a way? Normally, typical values are around this order of magnitude. A cell needs to drain at least 1 square kilometer to be a cell falling into a river stream. But this is a parameter, and so it's something you have to tune. How could you tune this information? Do you have any ideas on how you could do that? Imagine that together with the digital elevation model, the representation of the topography, you have underneath also an additional source of information. For example, a satellite image. From a satellite image, you see if there's vegetation or if there's cobblestones and water underneath. If you have permanent vegetation like trees, of course you are still on a hill slope, you're not in the river. If you instead start seeing the river itself, or the spring, or some stone, parts of the riverbeds, it means that beneath your cell there's a river. So you fine-tune this number, and you might find out that in order to be more accurate, you have to use 16 instead of 10. If you increase the critical source area, you move downstream. If you decrease it, you move upstream. You can expand your stream network or reduce it in length using the critical source area. And we will see an example. Is it sufficiently clear what I said? This is a parameters. It's not, let's say, dogma that we receive 1 square kilometer because my professor said that, because critical source area depends on the climate of your region and the geology of your region. The least permeable your catchment, the smallest the critical source area. The more permeable the catchment, sandy hills, for example, the higher the critical source area. So it's a parameter you have to fine-tune depending on your geological and climatic region. And the way to fine-tune is to have in the background some information that tells you where the river is. Maybe pictures taken from above, for example. Okay? Very good. Last thing I want to show you is how we saw how we extract a river network from a digital elevation model. Let's see how we identify the watershed draining into one point. In this case, we need really basic information. We need the drainage direction grid, the raster that we just applying the D8 method created from the digital elevation model, and the point where the river cross-section is. So we set where the river cross-section of interest is, and then using that, it's called like this in the literature, Salmon algorithm, because it moves upstream. It follows a drainage direction raster to identify all the watershed that drains into one point. Okay? So for extracting the river network, you need to set a parameter, that minimum contributing area, that threshold area. In order to extract instead, delineate the watershed draining into one point, the only thing you need is the drainage direction grid and where the point is. Okay? Of course, in this example, we assume that the overall watershed is the topographical watershed. We are saying nothing about the possibility of groundwater to flow where the star is, which would complicate things, as if the surface was totally impervious, okay? Which is standard practice, but this hypothesis, simplifying assumption, needs to be tested. It's very complicated to identify the groundwater catchment. This is a way to identify the surface catchment, surface water catchment. Okay? And then, of course, you have a subdivision into watershed and some other information below, local slope, for example, using a tool that is called zonal statistics, you will be able to characterize catchment and identify, for example, the average slope of the catchment. So the tools we will be using will be the D8 algorithms. This will help us extracting a river network and delineating a catchment. This will be the first tools. And another tool, once we identify a subdivision of the study area to catchment and sub-catchment, zonal statistics. You have a raster layer below and your polygon above. For example, the raster layer is a representation of the mean annual precipitation, and you can compute the mean annual precipitation value inside the polygon. That will be your catchment scale mean annual precipitation. Okay, sufficiently clear? So the main objective of the practical application that you can already have a look at, if you go to Virtuale, there's a step-by-step PDF document that guides you through the application of the algorithms and the data set we will be working on as a zip archive. You can download them already, store them in a folder, which will be our working folder on Wednesday. And the main objective would be, let's start from a DM and a point where the cross-section is. Let's identify the watershed for that point. Let's compute the area. And let's also characterize this area in terms of catchment descriptors, like those that we use in the RStudio activity. Okay? See you on Wednesday.